We're going to continue our math break with some more review of some mathematical principles that will be necessary to understand elliptic functions. But I'm going to walk the dog all the way from the beginning, and we're going to go back to reviewing something from second semester calculus, the integration of rational functions. And it's not taught with this much completeness necessarily or systematically in second semester calculus, but nothing here is beyond mathematics beyond second semester calculus. So let's begin with the idea of what is a rational function. And the rational function is a ratio of two polynomials. In this case, our dependent variable will be x, and the numerator is a polynomial of kth degree in x, and the denominator is a different polynomial of the nth degree in x. And that ratio is what we call a rational function. Now, rational functions can be quickly simplified in principle. We learned polynomial division in our high school algebra class. So we know that all these rational functions can be ultimately written as a polynomial plus a remainder polynomial. And that remainder polynomial would be some remainder q, and we always put that over the denominator polynomial. The 2x squared plus ... and I guess what we have BLXL. So we start by understanding that any rational function can be broken up into this term. So now the idea is we want to be able to integrate any rational function of x. And we want to understand how much do we need to know in order to pull off this in complete generality. What is the core pieces of information which, if I don't know how to do it, I can't get this done? And it turns out that those core pieces of information, well, it really kind of depends where you want to stop and say what's the core pieces of information. But every one of these functions can be integrated in terms of elementary functions, meaning functions that we've studied previously in elementary calculus, or elementary transcendental functions. But let's see which ones we actually need and how far we can go to prove what this core level of knowledge is in order to integrate every one of these. And the reason we're doing this is because we're going to use the same principles to help us understand how to integrate functions that are rational functions not only of x, but also of the square root of a quadratic, of an arbitrary quadratic. We're going to study what is the basic machinery for that. And then once we study that, then we'll be ready to study the question about integrating this, where this is actually a quartic equation. So it would be something like ax to the fourth plus bx to the third plus cx squared plus dx plus e, all under the radical. And these are where the elliptic functions live. So in order to fully understand and comprehend this, we're going to walk ourselves from here to here, and this is where all of the inverse trigonometric functions are required. And then we're going to go here, and that's where we need to know the elliptic functions. Okay, so let's begin. Now, obviously, if we want to integrate this, we need to integrate this and integrate that. This one is easy. That's just a polynomial. We can integrate polynomials without any trouble whatsoever. So we're not even going to worry about that. So now all we have to do is focus on this, where the degree of q will always be less than L, right? The degree of q is going to be less than the degree of the denominator because that's what we get after we do the long division. If k is larger than L, we're going to end up with a regular polynomial plus a remainder term, where the definition of a remainder term essentially is that, well, not the definition, but a requirement is that the numerator has a lesser degree than the denominator. So now we need to focus on just this part here. Well, this part can be rewritten in the following way. This is the way this ratio can be now expanded. You take this qx, it's a polynomial, right? So here's the polynomial. It's a kth degree polynomial. And the bottom is a polynomial L. Well, a polynomial, and we're considering it at x as a real variable now. Very often when you read this material, x is considered a complex variable, and that actually kind of matters for the analysis. But as a real variable, this polynomial will have L roots. and whatever those roots are, we can express them this way. The real roots will always be expressible as a factor of x minus the root, raised to some multiplicity, n1, which is very often 1. It's pretty rare that that's larger than 1, but we're going for full generality here, so it could be any number. And there'll be h of these real roots, and then the complex roots are bound up in these quadratic terms, these irreducible quadratics. That can't be factored into two real roots. These are the complex conjugate pairs, and they also come with a multiplicity. So now we need to be able to integrate this, as I just explained over here. Right? I said a moment ago that we've got to be able to integrate this and this in order to integrate that. So this we know how to do, so this we have to integrate. So now we have to be able to integrate this thing. Now, this is just attacked with the method of partial fractions. So this is a review, right? Everybody should know or remember partial fractions. But fortunately, we're not going to actually pull this apart with real partial fractions. All we need to know now is that in principle, it can be done. And so each of these pieces, each of these factors with their multiplicity is going to produce a contribution to the partial fraction sum. And this part, for example, is going to produce something that looks like this. It will have n terms, or n sub 1 terms, because this is the first root. So the first root has multiplicity n sub 1. It's hard to, the symbolism here is to do everything fully general is actually kind of annoying and difficult. So r sub 1 is the first real root of this denominator, and n sub 1 is the multiplicity. And that real root, with its multiplicity, comes down here. Since it has a multiplicity of n, we're going to get n terms, each with a higher power in the denominator, right? The root's going to show up as a higher power. Here it shows up as linear, here it shows up as a square, and then here it shows up as the n1th power. And there'll be some number in the numerator for each of those cases, which we call h. And this is going to be the contribution just of that root. And remember, if that was a 1, then these terms would be gone, and the only term that would live would be this term, right? And that's very common when we practice this, that when we first learn how to do this, that's the common condition. But we'll get a string just like this for each real root, right? This real root will contribute its own thing. It would be h1 prime, and then it'll be x minus r2 plus h2 prime, x minus r3 squared, etc., right, for this root. And every real root will give you this string. Notice we'll run out of symbols if we try to keep doing this. It'll be h prime, h double prime, and that'll be moving from root to root to root. I should give some number here, right? This h is the first coefficient for the first root. Maybe I should give it a superscript or a script over here or something to designate that. But it's not that important, because what this is telling us is that we have to be able, to integrate. Ultimately, to integrate this, we're going to have to be able to integrate that, because this big thing here is going to become a large sum, and each of these factors is going to contribute a sum. Now, these guys here contribute a slightly different sum, right? They're going to contribute, let's look at the first one. Actually, the first one will be, the first one will be d1 x squared plus e1x plus f1, and then it's going to have I1 x plus j1. So for these squared terms, for the terms that are quadratic in the denominator, right? That's these guys here. These guys that represent the complex roots of our denominator polynomial. Those guys will show up with linear terms in the numerator, but otherwise it will be just the same. There will be an I2x plus j2 over, and then here it'll be d1 x squared plus e1 x plus f1 squared plus dot 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 all the way to you get to the n1th term, right? But each time it's linear on top. So each of these guys is going to contribute a sum that looks like that. So ultimately, in order to say that we can integrate all rational functions, we know we can integrate polynomials. We're working on integrating this, but integrating this is equivalent to integrating expressions like this, which are basically, in general, expressions like this, right? Where n could be 1 to any integer, right? Integer n. And we also, definitely need to be able to do that, and we also need to be able to integrate these things. So we need to integrate polynomials of arbitrary powers in the denominator, quadratic polynomials, and linear terms in the numerator. All right, so let's see if we can quickly do this guy here. That doesn't look too hard. Well, that's the integral we want to do. To integral some constant h over x minus r to the n, and the trivial substitution of just u equals x minus r and du equals dx, we end up converting this interval right away into h times 1 over u to the n du, which immediately integrates to this easy to figure out expression here, and the natural log. In the case that n equals 1, it's the natural log, right? That's the definition of natural log. We'll have a little more to say about that in a moment. But this is easy, and then you have to just substitute back this x minus r, and then you'll get, and with the final substitution, this is what we get. So this one is actually really, really easy. But it goes a long way, right? I mean, if you don't have any complex factors, then that's really all you need. So we can integrate that, and that if there were no complex factors, we'd be actually done. Because there's no linear factors up here, so we don't have to worry about integrating h1x over this. All these real factors contribute is at worst something that looks like this, which is at worst this trivial elementary integral, which is not only second semester calculus, but it's like the first thing you learn in second semester calculus. Okay, so that leaves these guys, which are indeed a little bit trickier. So this is the general integral that we have left to do, meaning we've hammered our integral of, well, I shouldn't put an equal sign there. What I want to say is we hammered our integral of our rational function of x into a bunch of different things. An integral of a polynomial, check. An integral that looks like this, check. Now what's left is these integrals here, which obviously can be split into two parts. It can be split into the integral of m times x over this quadratic term to the p power, plus the integral of just n over the quadratic term to the p power, right? So if we can do those, then we're done, because that will be everything that we need to integrate every rational function of x. So let me just start by writing down the answer. I can look this integral up in a table and give it to you, which I'll do now. And here it is. Notice that the polynomial in the denominator is defined with a 2b there, a 2bx. There's a good reason for that. It just simplifies things. But I've used the form, this form I've used, of all the notation and everything is identical to the canonical reference, Gradstein and Risdick, which is a table of integrals, series, and products. And it's number 2.103, equation 3. And this is called a reduction formula, because you'll notice, I guess it was a little bait and switch. I said, I'm going to give you the answer to this integral, and then I give you an expression that actually has another integral in it. So I didn't really give you the answer for the integral, but what I have done is I've given you the integral from that takes the denominator p. You have to calculate this big mess, which is everything here is these are the coefficients of the expression, the coefficients of the numerator, right? Everything here is known. P is the order of the quadratic. So you can calculate this number here, and then to that you add, and you calculate this number, which is the coefficient, but then you have to calculate another integral. But that integral is 1 degree less. It's the same. It's actually one. Not only is it 1 degree less, but it's also without. It's like m plus x plus n, but m is 0, right? It's just n equals 1. So it's the same formula with m set equal to 0. So it's a reduction formula because it reduces the order of the integral you have to deal with. But on the other hand, it has to bottom out, right? When p equals 1, you're going to get a 0 here, and this doesn't work for that case. You have to know the p equals 1 case. In other words, if p is 1, you don't use this formula. Now, when p is 1, you actually have to do the integral for p is 1, and then you have this reduction formula which will bottom out. So we have to keep in mind that we still need to do this integral for p equals 1. We still need to know that. But we've made some progress here. But then again, have we made progress? I mean, we've looked up the integral, and my philosophy is if you need an integral, yeah, look it up. Use it if you have to, but you better figure out how to take the integral. Set aside some time, anytime you run across an integral where you use Gradstein and Risdick or some other reference, rederive it. And even if it's one you've forgotten, like here's a good example, the integral of secant theta, right? Say you needed that integral. Well, you can look it up and get the natural log of secant theta plus tan theta plus c. But it's totally worth your time to go back to your elementary calculus book and study how to do this. So we're going to keep in mind that we really do want to outline how this recursion or reduction formula is actually calculated. But let's get back to the case, the more important question at hand, which is how this thing bottoms out. And that'll help us with the reduction formula too, actually. So the basic trick for these quadratic terms is to make the substitution u equals x plus b over c, or it'll actually end up, the literal substitution, if you exercise, of course, will be x equals u minus b over c. And if you do that, if you use that substitution, you will end up converting the quadratic a plus 2bx plus cx squared into c times u squared plus or minus d squared. And a few things are important to remember. The c, don't forget the c out here, right? That's the leading coefficient on the x squared. Gradstein and Redzig writes it backwards. Usually you're used to a squared plus b squared plus c squared. Well, here it's a plus 2bx plus cx squared. Totally superficial, but this 2b isn't superficial, but what that does is that takes this discriminant piece and kind of gets rid of all the 2's and the 4's that you see in there, and it cleans it up a lot. At a price of putting a 2 in the polynomial, in the quadratic itself, which normally isn't there. But if that 2 wasn't there, it would show up. It would show up here. It would show up over here somewhere. The plus or minus is totally dependent on the sign of this thing. We're going to say d squared equals this guy here. Let's see, does that make sense? Hold on. Actually, I think the way we want to say this is d squared is equal to basically the absolute value of this. The plus version comes if we have CA is greater than b squared, and then the minus version will have if b squared is greater than CA, right? And that's where we'll choose between this plus and this minus. So if you make that substitution, if you execute that substitution, what do we get? Well, we get this elementary integral, right? This elementary integral. And it's elementary because, although you may have forgotten, this is one of the ones you probably memorized at some point in time in Calculus 2. And this elementary integral has two solutions to it, one for the plus and one for the minus version. Let me shrink this part down here. and move it there so I can write the plus and minus version. And this elementary integral breaks down to these two possibilities. The plus possibility gives you this inverse tangent function, which we'll have more to say about in a moment. And this, the minus version gives you the little more complex natural log of this ratio. And now, of course, the last step, these u's should be, these x's here should be u's. But the last step is just that. It's to substitute back for u, substitute this guy back. And ultimately what that's going to give you is, and if you finish that substitution, this is what you get. And it's a big mess, but it's definitely worth working through. And you can find these expressions also in grad student arithmetic, the way I've written them out here. So, but the basic trick when you start seeing these quadratics in the denominator and you're dealing with real functions is to make this substitution and convert it into this form here. And that form we know. Now the question is how do we know about this integral, right? If you stick to what I said, remember what I said about secant, you should study the secant integral. Well, you should study the integration all the way down till you remember exactly how it was done. Now you can have this kind of memorized, I suppose, and say, it's good enough for me, and I'm not going to complain. But in this particular case, in this particular lesson, drilling down to how this integral is done is actually worth our time, because we will see a technique here that will be used for the elliptic functions in a moment. So we will be reviewing that in a moment, but we're still going to continue on with our program of integrating rational functions. So far we've gotten this guy down, which is important because remember that is the bottom of this reduction formula. So if we have the bottom of the reduction formula and the reduction formula is just algebra and another integral, which will be more algebra and another integral and more algebra and another integral until finally you end up with that bottomed out or base case of the recursion. It's really recursion with a base case. And that base case is going to be this integral here, which is ultimately an inverse tangent function. Oh, so wait a minute. That integral, get down to the base case, right? We can do that. We can do this. And all we have to do are this and this. Yeah, okay, so we're done actually. Okay, so we can now integrate every rational function. So, but let's take a quick moment and then do what I just suggested and look here at this thing. One more thing I should point out is there's two options here. It looks like there's two options. There's this option and this option. Now, it turns out if this is the case, right, if AC is less than B squared, that's effectively the discriminant of the problem. And this is the discriminant that would apply for real values of this solution. So, but if we had real roots to this equation, if we had two separate real roots, we would have decomposed it way back in this phase here, and it wouldn't have been a quadratic. It would have been another real root, and it would have come to us in this form, and we would have used this expression and ended up with the log right here. Now, what this is telling us, though, is if we walk this all the way back, is this thing, under this circumstance, has two real roots, and you're taking the difference of two real roots, so you get a log minus log, which is the log of a ratio. And you can actually prove to yourself that that would be the equivalent of breaking it down into two separate real roots, doing a partial fraction, taking the integrals of two partial fractions, ending up with two logs, taking the difference of the two logs, and coming up with a ratio. You'll end up right back here. So this entire case is actually superfluous to our problem at hand, because when we're here, we're actually under the assumption that this is the condition. Because if this was the condition, like I said, we would never have gotten there. We would have just added two extra real roots here, and we would have used this material. Okay, so now I wanted to talk a little bit more about this integral. We're actually going to look at it in this form, a much simpler form. Well, it's really not much simpler, right? We're going to take the plus, right, and with the plus, and we're going to take D to be 1, and we're going to take C to be 1 too, all right? So it's not a much simpler form, but we're going to take it to this essential form. This thing is handled by a clever trigonometric substitution, which is one of the second semester calculus substitutions we all should remember upon seeing again. And let me write it down here. We have u is going to be tan theta, and du will be secant squared theta d theta. The derivative of tangent is secant squared. And then we have the Pythagorean identity. Remember, there's three well-known Pythagorean identities in trig. Cosine squared plus sine squared equals 1 is the most famous, but you also have this one, tan squared plus 1 equals secant squared. So with these three things, if I make those substitutions here, I can convert this integral into an integral with trigonometric functions. The first step being the straightforward substitution, where I'm substituting for d, well, I keep writing dx there, that should be du, where I substitute immediately for du with this, and I get this, and obviously the denominator is equal to secant squared, so this I could just write secant squared theta down there, so it's just 1, right? So this ends up being integral of d theta, which is going to be theta plus c. Now this is the point. The point is now I have effectively the following statement. I have this thing. And imagine for a moment that I do know that u equals the tangent of theta. But I may not, maybe say, imagine for a moment I'm not really aware of the inverse tangent, right? Because what I want to write is the inverse tan u equals theta, and then make that substitution. So this integral ultimately is inverse tan u plus c. So my integral, 1 over u squared plus 1, is inverse tan u plus c. Now, this makes perfect sense if I know about the inverse tangent function. Let's imagine for a moment that I know about tangents, but I haven't really figured out about inverse tangents. I could still dive in and make this substitution, right? I'd still get all to this point. And then this last step, I'd say, oh, you know what? I need an inverse tangent function. Well, the thing exists, and I do know a few facts about it. I know, for example, that the inverse tangent of 0 has got to be 0, right? Because I know that the tangent of 0 equals 0. I know that. So at least I know its value at one place. So it turns out if I define the inverse tangent in the following way, see, I know whatever it is. If I just give it a name and finish up this expression with a name, I know that by the fundamental theorem of calculus that this is going to be the inverse tangent of x. It's by definition. This will be the inverse tangent of x. It's a definite integral from 0 to x. We'll notice that the argument of the inverse tangent lies in the limit of integration of this integrand. And that's how we would define the inverse tangent of x. Because if you look at this, the fundamental theorem of calculus tells us if this is the case, then the derivative of the inverse tangent is going to be 1 over x squared plus 1. That's by the fundamental theorem of calculus, right? So the fundamental theorem, T-H-E-O-R, oops, too many letters there. Theorem of calculus. And just as a reminder, I guess I'll put it down here, that the antiderivative of f of t is equal to, if it's equal to this thing, right? And this definite integral. And that's what the antiderivative of little f is defined this way, and that demands that the derivative of big F is equal to the integrand as a function of x. And notice how x lies in this limit of integration. So that's the fundamental theorem of calculus. So we can look at this two ways. I can say, oh, you know what? If I want to integrate any rational function, and now I'm going all the way back here, I have to know a few things. I have to know how to integrate a polynomial, check. I have to know how to integrate this guy here and likewise that guy there, right? For the n equals 1 case and the n does not equal 1 case. Check. I need to be able to integrate this and get all the way down here to this bottom case. Well, I understand this recursion relation. That's not a problem. And then lastly, I need to be able to integrate the bottom case, which we did, but the bottom case kind of depended on my being able to integrate this. Well, what if I don't know how to integrate this? Well, then I can say, at a minimum, all integrals of rational functions come down to integrals I can do, and then this hard one. And I'll give this hard one a name. I'll call this one inverse tangent of x, because it turns out that's what it is. And then I get real familiar with it, and then I just sort of add this to my list of elementary functions, and now I then say to maybe my students after I invent all this, I say, oh, the inverse tangent's an elementary function, and we can take the integral of any rational function in terms of elementary functions. And in particular, inverse tangent is important, and natural logarithms are important, right? Natural logarithms from back, where were they? Right here. Natural logarithms are important. So that's and of course polynomials are important. But I can do it now. But before I knew about inverse tangent, I would have to sort of stop at this integral and say, well, I can put it in terms of this integral, right? But once I am comfortable with this integral, this can actually define the inverse tangent. In principle, I can numerically calculate this integral and calculate values for the inverse tangent. Okay, so that's an important thing to remember. We're going to see this a couple more times. We'll see it for sine and cosine in our next lesson, and then eventually we'll see it for the elliptic functions in the lesson after that. Now, the last thing I want to point out is, what about this beast, right? This beast is really where most of the magic happens if the rational fraction you're dealing with has complex roots to more than 1 degree, right? If it doesn't, you'll never see this or use this. But if it does, how do you calculate this thing? Well, we're not going to do the whole thing, but it's an integrations by parts problem. And I'll give you a hint. The first thing you do is you make the substitution to convert this polynomial into the CU, well, it'll always be a plus, right? Because, like I said before, CU plus U squared plus D squared form. So the denominator is going to end up looking like that when you're done. And you're going to substitute also for the x up here. So once you've done that, you've converted this integral here is now converted to something that looks like the integral. There'll be some collection of constants out in front, and you'll have one integral that'll look like this with u squared plus d squared du, and then plus another integral with a bunch of constants out in front, which will be just du over, oh, this will be to the to some power n, u squared plus d squared to the power n. So you're going to end up with these two integrals, and they're different, right? You've got a u up top here and no u here. The one with the u up top is completely trivial to integrate because you can just use the substitution w equals u squared and dw equals 2u, and then you end up with 1 over u to the, or 1 over w to the n dw with some, I think, a half out front, right? So that's trivial. So this one is done. This one, it's a bit harder, but you proceed with integration by parts. And what I'll do is I'll just tell you what the substitutions are. If your model for the integration by parts goes like integral of w dz equals wz minus the integral of z dw, if you were to use that as your symbolic model for the integration by parts, then you would take w, after you do the conversion to u plus t, you take w equals u squared plus d squared to the minus n power, and then dw you would take to be minus n u squared plus d squared to the minus n minus 1, right? And then dz would equal du, and z equals u, right? So these are the substitutions that you would use to construct the integration by parts. And if you do that, and you work it completely through, what you'll end up with is you'll basically end up with an expression that can be converted slowly and deliberately into this expression right here. And you can see, right, it has an integral over here. Well, this integral here is going to be the reduction integral in the end. And what's important is, I think in the final form, it's really kind of hidden. You actually end up having to take this integral and put it on this integral. Well, you have to take, I think what has to happen is, let me see if I remember right. This integral here, actually, this guy ends up being the new level of recursion. This guy here, I think, ends up being this guy here. And you have to shift the exponents to make that all happen. So it's not totally trivial. It's a little bit complicated, but at the same time, it's still just an exercise of this integration by parts with this substitution. In other words, you go through and execute this integration by parts with this substitution for this integral, and you will get this answer eventually. Ultimately, of course, you have to substitute back for the u to get all of these coefficients, because these coefficients all come from the numerator and the coefficients of the quadratic. Okay, so the important thing we learned here is we kind of got our feet wet, or our hands dirty. We got our hands dirty about how to integrate rational functions. Now the next two lessons are going to be rational functions, but we're going to add an additional piece to it, a square root of a quadratic, or of some kind of quadratic term, bx plus c, like that. And that square root will be littered into this, peppered into these two expressions on the top and the bottom. And we're going to see how to integrate all of those rational functions. And those guys are going to be called r, x, and then square root. I guess the way we were doing it is c plus 2bx plus ax squared. I may not keep that notation for the next lesson, just to be flexible. This is how Gradstein and Rizdik does it. So I stuck to that so you could refer, if you felt like it, you could refer to the book. So the next lesson is now rational functions of a different form, of this form. And of course, those are going to be the rest of our trigonometric, logarithmic integrals. We'll be able to solve all of these also. The problem is when we take this and we turn this into a quartic, when we go c plus 2bx plus ax squared plus, I guess, a prime x cubed plus a double prime x to the fourth. That guy, if you put that in there, now we are in the realm of elliptic integrals. And we'll talk about that probably not next lesson, but the one after that. Okay, see you then.